Mr. Yong also will explain to us about application of construction stage analysis in building structural design. And without waiting any time, please welcome Mr. Yong Ilso to the stage.
Hello. Nice to meet you. My name is Suo. I'm in charge of a technical manager for building engineering. In today's webinar, I will share the technical items for construction stage analysis. I will talk about the following 3 topics today. First, construction stage analysis in low-rise building. Second, column shortening in high-rise building. And last, project applications with construction stage analysis. First, I will introduce the elastic construction stage analysis in the design of low and mid-rise buildings. First, let's check the analysis results of the example model with 10-story. In the example model, the core wall is located inside, and the outside is composed of RC frame as follows. Let's check the moment for a section containing a core as follows. The expected moment diagram of beam is as follows. Since the bending stiffness of the core is greater than the column, the beam moment at the core will be slightly larger than moment at the column. However, the actual analysis result showed that the moment at core wall increased more and smaller at the column, as shown below. The moment at the middle of beam also had a smaller value than expected. Why is it different than expected? The first cause is differential shortening of column and wall. In the case of a wall, the lateral load is an important factor in determining the cross-section. Therefore, the ratio of compressive strength to axial force is generally about 15 to 20%, so it is very small. However, in the case of columns, gravity load is the most important factor, and the ratio of axial force and compressive strength is about 40 to 50%. Therefore, a greater vertical strain occurs in the column than in the wall. For this reason, an additional member force is generated in the horizontal member by differential shortening. The second reason is that there is an error in the conventional analysis for building with story. In case of the conventional analysis, as shown on the right, the loads are applied at the same time on all story. And in case of considering the construction stage, as you can see in each stage, the vertical and horizontal members of each story are constructed according to the plane level, even though deformation occurred in the lower story. So, the conventional analysis generates a larger deformation than the construction stage analysis, which generates a larger additional member force. In conclusion, the error occurs because conventional analysis does not take into account the structural characteristics that occur during construction. And to design safely, other solutions such as construction stage analysis should be considered. Therefore, in the case of conventional analysis, a large relative displacement between the core wall and column cannot be considered, and the large member force is added as follows. So we cannot design normally under the conventional analysis. Let's check the results of conventional analysis and construction stage analysis numerically. And then, assume that the structure has the same story height, the same load, and the same axial stiffness as shown on the left. First, it is a case of analysis that does not consider the construction stage. In stage 1, deformation of 1 occurs in level 1 due to the load on the level 1, and deformation of 1 occurs automatically in level 2 to 5 due to the deformation of level 1. In stage 2, due to the load acting on level 2, level 1 and 2 have deformation values of 1 and 2, respectively, and deformation of 2 occurs automatically in level 3 to 5 due to the deformation of level 2. The same analysis can be done for stages 3 to 5. Finally, the deformations can be combined like this. From level 1, deformations of 5, 9, 12, 14, and 15 occur. Among them, the following triangular box can be distinguished into the deformation by the deformation of the lower level. The right is the case considering the construction stage. Since only the deformation due to the force acting at each level occurs, the deformations from level 1 to are 5, 8, 9, 8, and 5. Interestingly, the greatest deformation occurred in the middle story. In conclusion, the deformation caused by the deformation of the lower level is removed, and at the level 5, the deformation is reduced to about 33% of the conventional analysis. After all, the member force of the conventional analysis includes a large additional member force due to the relative deformation of the column and core wall as follows. Therefore, when designing with this analysis result, there will be problems with the safety and usability of the structure. The following is a comparison of the conventional analysis and the construction stage for the example model. In the case of the axial force of the column, a difference of 3% occurred. The moment of the beam had the difference of about 300% at the column side and 14% at the wall side. In the case of the shear force of beam, there was a difference of about 10% at the column side and 6% at the wall side. Although there will be differences depending on the plan shape and the number of story, it is recommended to perform a construction stage analysis for accurate design of low and middle building. The following is about the evaluation of column shortening in high-rise building. Column shortening means a technical task that evaluates the vertical deformation of a vertical member in consideration of time-dependent material properties. When an axial force acts on a concrete element for a long time, a concrete element will have elastic shortening by loads and inelastic shortening by non-homogeneous properties of material. In the case of elastic shortening, as you know, it is caused by gravity loads. And inelastic shortening is due to drying shrinkage and creep. Inelastic shortening occurs larger in RC high-rise buildings. And there are different shortening according to the vertical member type, like columns and walls. In particular, different shortening between vertical members cause a lot of problems in high-rise building. If we look at the case of a high-rise with 100-story, in the total shortening of vertical member, elastic shortening accounts for 40 to 50% and inelastic shortening accounts for 50 to 60% generally. Concrete columns usually have a shortening of 2 to 3 millimeters per a story, so the shortening at the roof is about 200 to 300 millimeters. The shortening of wall is about 1 millimeter per a story, and the shortening of the roof is about 100 millimeters. Therefore, the different shortening between column and wall is about 100 to 200 millimeters at roof. It means that when the span between column and wall is 8 meters, it has a very large inclination of L40 to L80. Then, what are the problems caused by different shortening? First, it causes usability problems such as damage to finishing materials due to deformation as follows. And the additional member force is added to the horizontal member due to deformation caused by different shortening. This causes safety and serviceability issues like cracks, as described earlier. Let's take a closer look at the usability problems caused by column shortening. Absolute shortening causes the problems such as a bending of elevator rails, deformation of door frames, and damage to vertical finishing material. And the relative shortening causes the problems such as damage to the external curtain wall, reverse slope of the plant piping, a damage to the partition, and the floor finishing material. The causes of differential shortening have already been explained in session 1. Additionally, differential shortening occurs between column and column, when if the column cross-section is determined to be larger than structurally required by other factors, such as architectural needs, the axial force ratio is reduced. And in this case, the large differential shortening may occur even between columns. As described on the previous page, to obtain and reflect the correct additional member forces in the design, it is important to calculate the correct shortening through the program. I will introduce a shortenings of a typical RC building with 40-story. As can be seen from the following graph, the different shortening due to drying shrinkage and creep accounts for about 55% of the total amount. The conventional analysis shows an error of up to 23% in the difference shortening and up to 15% in the member force of the girder. So what is the solution for a differential shortening? First of all, the serviceability problem is solved through correction when pouring columns and walls. The pouring level of the vertical member is corrected so that the final shortening reaches the planned level and has a similar level to each vertical members. For this, it is important to calculate the correction value exactly. If the predicted shortening does not occur after correction, problems may arise due to correction. Next is the solution for additional member force. Since this does not remove by correction, the additional reinforcing bars must be calculated through CS analysis at the design stage and reflected in the drawing. Let's look at the configuration of column shortening again. Previously, I explained that the values in this area are the shortening values caused by the action of the load at the lower level. The deformation by these values are called up-to-slab shortening, and the deformation caused by the load of the upper and current level is called sub-to-slab shortening. Let me explain in more detail. In the case of up-to-slab shortening, if the slab is poured horizontally according to the planed level, so it is a meaningless value. However, in the case of a steel structure, the column must be made longer by this shortened length. Sub-to-slab shortening is an important value, which causes additional force to the horizontal member and problems in serviceability. Therefore, it is necessary to correct as much as sub-to-slab shortening by the method described on the previous page. For steel frame buildings, the member length should also be determined by additionally considering sub-to-slab shortening. So, what are the factors that influence each shortening? In the case of elastic shortening, as you know, it is the load, the modulus of elasticity, and the cross-sectional area. Creep is affected by specific creep factor, load, loading time, elapsed loading time, volume to surface area ratio, relative humidity, and rebar ratio. And drying shrinkage is affected by extreme drying shrinkage, elapsed time, volume surface area ratio, relative humidity, and rebar ratio. The main model formula for calculating creep and drying shrinkage is as follows. Among them, General provides ACI and CB models, New Zealand, Australia, Russia, India, and European proposals. Key differences between codes are the restraint effect by rebar in creep and shrinkage, and progress pattern of drying shrinkage, according to increase in volume surface area ratio. Then I will introduce how to calculate the shortening. First is the calculation of elastic shortening. The formula below is presented by ACI Committee 209, and it is calculated by considering the elastic modulus at time acting the load. In here, the concrete compression strength, FCT, is calculated according to the curing method and time, as shown below, and affects the calculation of elastic modulus. The right graph shows the change of compression strength according to the curing method and curing time. Below is the creep strain calculation according to ACI 209. The creep strain can be calculated by multiplying the creep modulus by the elastic strain. The creep coefficient is calculated by multiplying the time function by the correction coefficient, as shown in the equation on the left. For correction, it is calculated by considering 7 corrections as shown in the table on the right. In turn, loading time, relative humidity, volume surface area ratio, concrete slump value, aggregate ratio, cement content, and air content are applied as correction factors. The graph below compares the curves of strain time for each proposed model. Although there is a difference by model, I think that it will not be a problem no matter which model is used, because it will be corrected through creep experiment and measurement in the construction site later. The following is the calculation of dry shrinkage strain. The formula below is for the calculation of a dry shrinkage strain according to ACI. The strain is also calculated by multiplying the time function by a correction factor. The correction factor is the same as creep. Let's look at the curves for the variables in the correction factor formula on the previous page. First, it is the correction factor according to the variable of pouring environment and the cross-section shape. When the factor is large, the strain increases. First is for the creep correction factor by 2h. As the age increases, the correction factor decreases. The second is for the correction factor by relative humidity. As the relative humidity increases, the correction factor decreases. Next is a correction factor by the volume surface area ratio. For example, in case of the column with 1 meter dimension, the volume area ratio is 250 millimeters. And for a wall with the dimension of 0.2 meters and 5 meters, the volume surface area ratio is about 100 millimeters. In the case of creep, the difference in factor is small, but in drying shrinkage, the ratio has an effect. The last graph is the correction factor by elapsed time. Next is the correction factor according to the concrete mixture. The larger the slump radius, fine aggregate content, air content, and cement content, the higher the correction factor value, which means that it causes a larger creep and shrinkage strain. Next is for the entire process of the column shortening project. In the initial structural design stage, the first construction stage analysis is performed by applying the basic inelastic material model and the assumed construction process. This is called preliminary analysis. In design step, reinforcement for additional member forces is reflected through preliminary analysis. Next, when the construction site is opened, material experiments are conducted. Through the experiments, we can obtain the curve of compressive strength, modulus of elasticity, creep, and drying shrinkage. Secondary analysis is performed by reflecting these experimental values and the actual construction process plan. This is called the basic analysis. Finally, the third construction stage analysis is performed in consideration of the changed construction process and construction environment. This is called main analysis. Through accurate prediction considering the measured shortening on the site, we have to make construction corrections for the shortening of the upper story that has not yet been poured. Let's look at what we need to consider in the structural design step. First, you need to control the arrangement and size of columns when designing the plan. Columns adjacent to walls are repositioned to have as long a distance as possible. And the size of the columns is determined so that similar compressive stresses are applied between adjacent columns. Next, through preliminary analysis, additional stresses occurring in the slab, beam, and lateral resistance systems, like outrigger or belt wall, are calculated, and rebar is added in these members. In addition, construction alternatives should be prepared for different shortening occurring at the connection between the high-rise and podium. And the connection timing and location are determined at the joints between the outrigger and the column, and between the high-rise and podium. The following is how to do a material experiments. First, a compressive strength test is performed in order to obtain the compressive strength and modulus of elasticity for a cylinder of 7 days, 28 days, and 90 days of age. And in creep experiment, we can obtain the specific creep strain curve from 12 to 16 weeks through the experiment. Finally, in drying shrinkage experiment, we can obtain an extreme shrinkage strain curve of about 12 to 16 weeks. These values should be reflected in the secondary construction stage analysis. In order to accurately predict the shortening, the results measured on construction site are reflected in the third analysis. Through measurement, the data are collected on site temperature and humidity at the time of pouring, initial curing temperature, and actual shrinkage by construction process and loading time, etc. This is reflected in the construction stage analysis. And it is possible to accurately predict the reduction amount by correcting the analysis reduction amount value by comparing it with the reduction amount by measurement. For the correction of the analysis result, the scale is adjusted to have a stain curve similar to the measurement value as follows. And we can get the accurate shortening at the target day through this process. The picture on the right shows the strain gauge installation. Next is how to do the correction. The column is poured as high as the shortening so that the slab level at the time of construction completion matches the planed level. Correction is done by grouping so that the difference between the correction value and the predicted value is within the allowable value as shown on the right. In general, correction is performed by groups in units of 2 or 3 story. The following is the progress of the column shortening project using general. First, create a group for members, loads and boundary elements in order to set the construction stage. And, according to the construction schedule, group information should be assigned to define each construction stage. Next, we need to define the time-dependent material properties, such as creep, shrinkage, and compressive strength, and links each defined material properties to each member. Analysis is performed using the defined construction stage and inelastic material information. We can obtain the member force for each gravity loads, creep, and drying shrinkage through this analysis, and can create a load combination including a wind and seismic load. Now, it is possible to do a design that reflects the column shortening using these load combinations. And the shortening of each vertical member can be obtained from the analysis result also, and the we can calculation the amount of correction using these shortening values. The following is an example for the construction stage analysis. It is the RC building of the 12th story. Please see below for the system, material, and applied load. The plan drawing is as follows. And the cross-sectional size at the bottom of each member is as follows. The right is a simple sectional drawing in B grid. The following is the construction schedule drawing for the example. The construction of the example building is carried out in units of 1 story, and the duration for 1 story is assumed 5 days. Self-weight is reflected at the same time as concrete is poured. In case of the finish loads, after the construction of structural member is completed up to the 10th floor, it is applied to the structure in units of 3 story from the lowest floor. Live load is applied to the entire structure, assuming to use the building after 30 days have elapsed from the day when all finishing loads are imputed. The following is a table that organizes information to create a model for construction stage analysis. The first column sets the name of each construction stage, and there are a total of 14 stages. It is set at 1 stage for each story, and the stage where live load is applied, and the stage where 3 years pass after the completion of the structural construction are added. And the following columns are information about the grouping range and name of the structure, boundary conditions and loads by each construction stage. And the right column shows the duration for each stage. First of all, it is a caution when inputting the floor load. Because the floor load is typically input without the distinction of load case, it is not possible to set the construction stage for each load case. Therefore, the COVID-to-beam load type option should be applied under the construction stage analysis. If applying this option, you can find that the floor loads are divided by load case in tree menu and load table. When the modeling is completed, a group should be created according to the construction stage table. If clicking the Group tab of the tree menu, you can find the group tree for structure, boundary, and load. If clicking the right button of the mouse on the group type and select New, a sublist is created, and you can modify the group name according to the schedule table. After creating all group names as shown on the right, you select the elements corresponding to the target construction stage. And then you can select the target group name and drag it to the modeling window. Then the elements are automatically assigned to the target group. Load group can be assigned by selecting the corresponding group name from the group column in the load table. Now, I will create the construction stage information in general. The page is an example of the settings for stage 11. First, enter the name and duration of the process by referring to the information in the schedule table. Then, click the Element Group tab and select the group corresponding to the stage 11, and click Add button. Next, click the Boundary tab and select the target group names and click Add button. Finally, set load in the same way. Of these, in case of DL2, the load is applied after 3 days from the start day of CS11, so day is set to 3. The next step is to define the time-dependent material properties. First, enter the name of the material function and select the code, and input the values for calculating creep and shrinkage strain according to the selected code, and input values for calculating correction factors. We can check the curve by the calculated function as follows by clicking Show Result button. To perform in second or third analysis, we can input the values from material experiment directly into this table. And the time-dependent material properties should be linked to the material of the member. Each time-dependent function and link information can be checked and modified in the tree menu as follows. This completes the model creation work for analysis. Before performing the analysis, you can set the following analysis environment. First, in the analysis type, we can select a linear analysis, non-linear analysis, and material non-linear analysis. And in the analysis of time-dependent material properties, set conditions such as iteration number and time step. And the control to pay attention is to set the load case to be distinguished from dead load. If not set, all gravity loads such as live load are included in the dead load, and only the result for dead load is output. General is supporting the load combination function in order to design considering a results of construction stage. When generating a load combination as follows, we can use the load case and creep and shrinkage loads, and you can combine an earthquake load and wind load too. Of course, it provides basic auto-generation of load combination. Final procedure is the calculation of the shortening value of the vertical member. General provides the shortening value of the creep, shrinkage and elastic shrinkage of the specific nodes as follows. It is provided a graph and Excel data. We can calculate the vertical correction value through these shortening values. Finally, I would like to introduce other engineering tasks that can use construction stage analysis. First, it is to check a crack caused by drying shrinkage of horizontal members. In the case of a horizontal member installed between the high-rise buildings like Case 1 or core walls as Case 2. In these conditions, strong restraint occurs at both ends of the horizontal member. And the cracks occur when tensile force is applied by drying shrinkage, as shown in the figure on the right. And it will cause the problems in the serviceability and durability of the structure. To prevent the cracks by dry shrinkage, we can install a delay joint as follows, and connect the delay joint after almost drying shrinkage occurs. Alternatively, the cracks can be prevented by adding a rebars at the predicted crack point found through analysis. The following is an example of Case 1. On both sides, the high-rise building is located, and a wide podium is located in the middle of the plan. Therefore, cracks are expected in the slab of the podium. To prevent cracks, the construction process was planned with a time difference by dividing the area into small units. And a delay joint was installed in the part where the high-rise and podium contacted. This is the comparison for the two analysis. Analysis 1 is the result without considering the construction process and joints, and Analysis 2 is the result considering the construction process and delay joints. When the stress at the target point was compared, the result of Analysis 2 decreased to about 35% of the Analysis 1, and it was evaluated that cracks did not occur. The next is an example of the analysis sequence for the example structure. Each construction area was analyzed in order, and after the entire horizontal member was installed, joints were connected and analyzed. Finally, it is the application of the construction stage in the underground structure. On the left is an image of the entire model. We can do the modeling and construction stage analysis according to the order of construction, like the excavation and the removal of anchors as follows. Through construction stage analysis, we can design accurate temporary elements and underground structures. Thank you.